Yeah, so welcome to the seventh lecture. So in the previous lecture, let me recall again. So what we have learned? We have learned the basics of MATLAB, plotting, conditional statement, loop, integration, differentiation, interpolation. Then we worked out a problem. Which is a real world problem, and we have learned how to incorporate this. Uh, how to incorporate MATLAB programming for real world problems. And we have also explored the CF toolbox, and also we learn how to do fitting to any of we can do the curve fitting, and we can extract relevant parameters and also dependency of a certain parameter on other parameter value. So okay, so today we will learn a very important topic, which is this technique is, one of the greatest invention you can think of in the last century. So this is Fourier transform. So basically, last century, and so Gauss finally. So Gauss initially proposed it, but at that time he was, not sure about. He was not aware of how important the discovery was. So in the and after that, so initially he proposed the Fourier transform. Then also he proposed the idea of fast Fourier transform. So which we will learn today. Then in around 1960, so for the regarding the regarding the issue of this atomic, and this nuclear testing, this fast Fourier method was invented. But okay, so let me not go too deep into the history part. So yeah, so let me first briefly tell you what is the idea of Fourier transform. So Fourier transform. Okay, so what is a Fourier transform? So basically, you can think of it this way. So for example, so suppose you have displacement data with time. This is displacement. This is time. You have this kind of data. Maybe this is how your data looks like. So for example, suppose this is the graph you are getting from the seismograph. So maybe you try to locate if there is an earthquake happening, so or not. So you are getting the data with time. So the brilliant idea of this Fourier transform is that so any response, any kind of response that you are getting, so it can be like this, or or any kind of response that you are getting from a signal. So you can decompose that into a summation or series of sinusoidal waves. So how the idea? So what is the idea there? So basically, you have this xt as a function of time. So you can write it as a summation. So of sinusoidal wave. So for example, suppose you have sinusoidal wave of frequency omega 1. So sin omega 1 t. Also, you can write it as a summation of plus sin omega 2 t, and you will have sin omega 3 t. And similarly, so up to a hot frequency you can go. So that is also limited. And also there is also sin omega, there will be cosine also, cosine omega 1 t, cosine omega 2 t, cosine omega 3 t, and so on. So let me show you a simple function. So instead of this complex looking response, suppose you are getting just a simple response. So for example, uh, these are my data points. Okay, so this is a perfect sinusoidal looking data point. Fine. So now I want to check if there is any component of, so I can draw a sinusoidal with different frequency. So how I can, so I can have sinusoidal like this. Okay, so I can have sinusoidal like this, or I can have sinusoidal like this also, and also I can have sinusoidal like this. Okay, so what I want to know, so I want to know what is the amount, what is the component of this sinusoidal. So I mean this will have a certain frequency. So what is the information in the signal of this frequency component? So I mean, so for example, suppose this is, I mean, your original signal. This is your original signal, and for example, suppose this is a 60 kilohertz sinusoidal signal. So you want to know what is the, I mean, portion of information that is there inside the original signal. I mean, what is the 60 kilohertz frequency information that is present? Then suppose this is, I mean, this is 60 kilohertz, and suppose this is, I mean, different frequency. For example, let us consider to be 80 kilohertz. So now you want to know what is the frequency component. I mean, what is the information in this original signal of this 80 kilohertz frequency. So in this way, so I mean, you want to know. So Fourier transform is basically you want to extract information about frequency component. So you have a real world signal. So for example, if this is your signal that you are getting, so you want to know in this signal what is the what is the percentage of 100 kilohertz. So is there any 100 kilohertz frequency component? Is there any 2 megahertz frequency component? Is there any just 10 hertz frequency component? So you want to know that. So whenever you want to know that, that means you have to do the Fourier transform. So the Fourier transform idea is that, so basically you multiply the original signal with each of the each of the frequency component. So when you want to know what is the information in the original signal of the 60 kilohertz, so what you will do, you will multiply your original signal. So which is your, this is your experimental signal. You will multiply this with the sine function of 60 kilohertz, and I mean you will, then you will, after multiplication you will get something, uh, some curve, and you want to know what is the area under the curve. So now what will happen if the if so for example, this is your original signal, this is the 60 kilohertz signal, and after multiplication maybe you are getting this kind of curve. So if you compute the area, then you will see that, I mean, if the original signal does not have any frequency component of this, so overall this area will, if you add up, this will be around 0. So you will get 0 in the in the output. So and that means your signal doesn't have any frequency component of the 60 kilohertz. So in that way, I mean, you can check with other frequency component also. So now I mean, so when it will match, so for example, when your original signal, so this, if, so this is your original signal, and you are, I mean, so multiplying it with this reference signal. So this is your reference signal, and the dotted one is your original signal. So now if we multiply these two, so in that case, what you will get? You will get a non-zero area. So maybe something like that. It will depend on the exact shape. So the idea is that, so whenever this is not matching, so whenever you have uh, sinusoidal like this, so overall, so if you, I mean, multiplied this for long enough time, then what you will see, you will get the overall area if you add up the area of the multiplication. So basically that will give you 0. And also I mean, so now this 60, so for example, suppose this is, I mean, this value, let us take to be 20 kilohertz. So now what you can do, you can consider an cosine wave also, so which is of 20 kilohertz. So if you take the area of this 20, if you multiply your original signal with this 20 kilohertz cosine signal, and if you want to calculate the area, so in that case you will also get 0. But so if this is shifted, so instead of starting from here, so if your original data has this value at t equal to 0, so let me plot here. So if this is your original data, so now you what you will do, you will multiply, for example, and suppose this is 20, this is 20 kilohertz but a little bit shifted. So you will uh, for a non-zero for a sinus sine wave with 20 kilohertz frequency. So this is your sine wave with 20 kilohertz frequency, and this is your cosine wave with 20 kilohertz frequency. So for each of these cases, if we multiply this signal with both of them, so you will get some amount of non-zero area. So if we look for long enough time, so it will be give you a non-zero value, and this will also give you a non-zero multiplication. So that is why you have to consider both the cases. You have to multiply with sine also, and you have to multiply with cosine also. Because if your data is starting from here, and if you are only considering the sine wave, so and if your original data looks like cosine wave, so if you multiply it with sine wave, then you will get your value to be 0. So if you compute the area, then that will be around 0, but that will give you a misinformation, because the response that you are getting, that has 20 kilohertz frequency, but since you the function, so the sine function you are multiplying with it, and that is phase shifted by pi by 2 with your observed value, so it will give you around area around 0. So you may think that there is no frequency component of 20 kilohertz, but actually there is. So that is why you have to consider both the sine and cosine. So and you have to multiply with both of them. So that is why it is so that is why it is important to multiply it with Euler function. So so we know what is the Euler expansion. So basically if we have I theta, so this we can expand this as cos theta plus I sin theta. So this expression we can use, and we can multiply what is our observed signal with this value. So and from the angle we can calculate what is the shift. How much the original data is phase shifted with our reference signal. So in that way you can measure the magnitude of your signal, and also you can measure what is the phase of your signal. So so now with this idea, let me write down what is the formula for computing this Fourier transform. So now, so the formula for computing this Fourier transform is this. So you have this time domain signal, and what you will do, you will multiply it with Euler function. So it is, let me write down here, 2 pi ft and dt. So and here you will have integration from minus infinity to infinity. So this is a continuous Fourier transform. So let me write down here. So why it is called continuous Fourier transform? So here, uh, this dt, it is infinitesimally small. So here you are assuming that the data you are getting, so the x data is, uh, precision is very large. So the data points are infinitesimally separated, so that you cannot, I mean, in real world you cannot separate them. But that is not the case in real world. So when you are dealing with any kind of experimental data, or even if you are looking at the screen right now, so the so there is, so you are looking at the screen, so you are getting some image. So that image, I mean, is stored in the form of pixels, and that are stored in matrix like form. So I mean, so all the data are essentially discretized. So I mean, whenever you want to compute the Fourier transform in programming, so that is why it is always essential to compute the discrete Fourier transform, because continuous Fourier transform or continuous process of taking data is not possible in real world. But okay, so let me show you how you can calculate the Fourier transform of any function. So let me take a kind of function. So suppose your xt looks like this. So this is your xt. So suppose this is t equal to minus a equal to a. So this is your how your function look like. So what is your function? So the function is basically and suppose this value is b. So your function has value b whenever t is between minus a to a, and your function has value 0 when t is greater than a and t is less than a. So for these two cases, your function has value 0, and in between this range your function has this value. So now you want to know what is the Fourier transform of this function. So then now what you have to do, you have to write down the, so f of omega. So I mean x, so so let me write down k here. So suppose k is in the, I mean, the transform domain. So this is a, in our x, so the okay, so this is t. Okay, so because I mean this as a function of t, so this is not x, so this will be t also. Here f of t, so f of t is b for t in this range, and it is 0 for in this range. So now what will be the Fourier transform of this f of t? So let me call it f of omega. I'm writing here capital F because this will be a different kind of function. So what will be the value? So I mean you will, so here you will have f. So how you will write it here? So this is your functional form. So you will write ft e to the power minus I 2 pi ft dt. I mean this is f or this can be omega. So let me just, in place of 2 pi f, let me write omega, or otherwise it will be confusing because we are calling the function also f. So I mean it is in the, it is the it is in the Fourier domain. So how, and the limit is from minus infinity to infinity. But so now I will change the limit. So minus infinity to a, you will have this function value which is 0. So this term will give you 0. Then you will have minus a to a, and in between this range you have your f of t to be b. So here it will be b, and you have your e to the power minus omega t dt, and after that you have from a limit from a to infinity. But for a greater than 0, again our functional form is 0. So this term will again give me 0. So essentially we are left with one term. So let me compute it. So minus a to the power I omega t d omega. So what will be the result? So it will be minus I omega t, and here we will have minus I omega. It will become minus a to a. So what will be the output? So it will be minus, or we can put I here, so I omega b. And first we will put a t equal to a, so which will give us e to the power I omega a. Then we will get I omega, and so if I now I can write down in the following way. So b by omega 2 2i e to the power I omega a minus e to the power I omega a. So I mean you can check it that if it is okay or not. So this is constant, and this is what? This is basically sine of omega a. So 2b by omega sine of omega. So f of omega. Now, so the function that we have taken, so this is how the function will look like in the frequency domain. So now if we put the values of omega, then we will know uh, what is the percentage of information, or how much information of that frequency is present in the original signal. Okay, so this is with the continuous Fourier transform, but I mean, as I have mentioned earlier, that real world, whenever you are dealing with real world data or something, so there is nothing called continuous data. So you have to, so whenever you are taking data, or whenever you're taking data through instrument, so essentially it will have a time step. So there will be a finite time interval between taking two data points. Also, when you are working with numerics, there also you have a finite step size. So there is nothing called continuous data. So you have to that is why it is important to know that we have to perform the discrete Fourier transform. So what is discrete Fourier transform? So now we will replace, so let me write down discrete. Okay, so so whenever you're, working with DFT, so we have to replace the the integration by summation. So I mean, when you want to compute the DFT, so for example, we have our x data in time. So we have suppose discretized data of x. So I mean, this is for n equal to 1, you have a value x1. For n equal to 2, you have a value which is x2. Then for n equal to 3, you will have x3, and n equal to 4, you will have a value. And so in this way, suppose you are getting 10 data points, so for n equal to 10, you have x10. So this is the points or data points that you are getting maybe from your experiment, or I mean you are collecting this data from somewhere. So now when you want to compute the FFT, so of this xn, so the formula is, so you have to write it as xk. So this is in the frequency, I mean Fourier transform domain. So what will be this xk? It will be from n equal to 0 to n minus 1 xn e to the power minus I. So this is an imaginary number, and here you have to write 2 pi k n by n. So look at the parameters. So n is, I mean, is a number of data points. So you will start from, so I mean 0, and you will go up to the n minus 1. So I mean in MATLAB, so I mean so essentially n0 means you are considering the first data point, and here you have to I mean put that n value. Then you will put n equal, you will put n equal to 0 1, which is for your second data point. And so here also n will be 1, and you will get a x value. So from that you will get a corresponding. So if we sum up all of that, then you will get xk. So how many data points? I mean, so how many times you have to perform this operation? So let us look at that carefully. So for each k, we have to do the summation for n number of data points. Okay, so I mean you have your x signal, and I mean you have your x values from your data, and this is I mean so you will sum you will make the summation for n equal from n equal to 0 to n minus 1, and that will give you value for a particular k. Now there I mean how up to how much k it can you can go. So basically I mean for in the k also you will have n data points. So effectively you have to perform this summation for n cross n times. Okay, so for computing this FFT, so what you have to do, you have to perform the same task n time, n into n time, so that is n square. So let me show you that in MATLAB. Okay, so first let me define the X range. So X, let us take some data points 2, 3, 4, 1. Okay, so this is our X. So this is how our X array now looks like. Then what you want to do? So I mean here, so for what is the n value now? So n is running from 0 to n minus 1. So I mean you have x and so let me create an array which will start from 1 and it will go up to 0. So let me call it uh, n, which will be from I mean start from 1 in steps of 1, it will go up to 10. So let me just check it. Okay, so you have this. Okay, so let me check their length if they're equal or not. Length of n, length of x. Okay, so they are equal. So I mean, suppose you have this data set. So so let me plot it, and so there is a function called stem. So let me check if it is in complex. Yeah. So what it is showing? So basically, for example, x for n equal to 1, you have this x value. Uh, I mean, so let me call it y and let me call it x. So this is your x array and this is your y array. So stem basically shows you, I mean, the values. So it doesn't connect with data points. So here you can see that for x equal to 0, you have this y value. X equal to 1, you have y value 0. For x equal to 2, you have your y value to be 2. For x equal to 3, you have your y value 3, and so on. So this is how your data points look like. So this is the signal. Suppose this is the signal that you are getting. Now suppose you want to perform the Fourier transform. So how you will do that? So uh, let me look at the formula of the Fourier transform. So you want to run a loop. So for each k, for a particular value of k, you have to run this loop, and you will also have to run a different loop for k also. So let me run the loop for k first. So for k to be from 0 to n minus 1. So let me define what is n. So n is the length of x or y, whichever you want to use. So this is the length, and then so for this range, for each of the values of the k, you have to run another loop for small n, so which is from 0 to n minus 1, and here what you will do, you will update. So you will update according to the rule. So this is your, I mean, xn. So you will use x. Now you are, what you will write here, n or n plus 1. So because, I mean, so in MATLAB, so whenever you are using an array, so generally index start from 1. So that is why you have to write here n plus 1. So this is your, I mean, n plus 1. So this gives you this number. Then you have to multiply it with the exponential. So how you will do it? So you have to write multiplied. So each element will be multiplied with exponential of minus 1 j. So I mean, it has inbuilt this j function. Then you can multiply it with 2, multiply with pi, multiply with k, multiply with n, and you will divide this thing with the capital N. So this is how, I mean, your this value you are getting, and what, and remember, you have to do the summation. So since you have to do the, I mean, summation for each of the n, so you can write, you can create an array initially. So for example, x man over x val or something. So it will be zeros 1 comma n. So you will write here x val. So it will give you the, okay. So let me think a little bit. Okay, so maybe you can use the summation function. So let me check for extend it. So let me write down a different function. So for n equal to 0 to n minus 1, what you will do, you will basically multiply x. So in your x, what is the element? Each element you will multiply with this, and you will do the summation. And so here you have to, so you can write here n should be from 0 to n minus 1, and this should give you the kth element. So x value means zeros, 1k I can write. And what is k? So k is n minus 1, and each of the values will be stored in x val k. Okay, let me think straight clearly. So this is what? So this is our, I mean, x array, which is I mean y array, which is our the values of that we are getting, and each. So this is element wise operation. So I mean we are multiplying each of the element with this function. So minus j to pi k, and here what we are doing, so each element we are multiplying with from 0 to n minus 1, and it will give us the summation. So we have to run a loop on k. So for k equal to 0 to n minus 1, so each time it will do the summation, and we have to store it in an array. So okay, so let us call this array, and this sum we will store in array. So let me check the output now. So let me check the length of the array. Okay, so if I write down the real, so it will plot the real part, and then I can also plot the imaginary part also. Okay, so yeah, so what we are doing here, so the first so let me do the pausing also, so that you can see which word is what. Pause, pause, maybe 1 second. Okay, so this is our data, and this is okay. So the blue one is our actual data, so which you are getting. So these are the independent parameters. So along, so we have this 10 data points, and for each of these data points, so these blue ones are the value of the dependent parameter that we are getting. So now after that, what we are doing, so here I mean we are looking I mean we are doing the discrete Fourier transform. So we are looking at the so what are the real part of, so if I mean go to the frequency domain, and so if our this real if our independent parameter has n number of data point, then also when we are Fourier transforming it, so in the transform domain it will also have along the x-axis it will have same number of data points. So it will have 10 I mean it will have 10 data point again, and for each of the data point how we will calculate the values, we are calculating the value here. So from by so here you can see, and since it is exponential, so it will have two parts. So I mean there will be real part and there will be imaginary part, and the red one represents the real part. And so so this real part, for example, this red point, how we are getting? So we are putting the k value 0, and then we are doing this summation for all these data point, and we are looking at what is the real part of this frequency component in our original signal, and what is the imaginary part. Then we are looking what is the real part and imaginary part of this frequency component in our original signal. So in that way we are calculating, we are looking at what is the real part and imaginary part, and if we want to plot the absolute value, so then we can do it with this absolute command. So let me pause again. This is the signal, this is the real part, this is the imaginary part, and this is the absolute value. So you can see what are the absolute value for this corresponding k values. Now, how we can convert the, so I mean this is how the discrete Fourier transform, I mean you can perform. So this is how I mean this value is computed, but I mean this can be done for small number of data points. So for example we have 10 data point, and this computation, I mean it scales as n square. So I mean if you have very large number of data point, so in that case it will not I mean it will not be too much it will be too much computational heavy. So that is why I mean so there is another Fourier transform, I mean so so I mean now let us try to look at the properties of this xk. So what is this xk? So I mean, can we? I mean, so is there any? So now we will try to find, is there any repetition in this n cross n time matrix? So I mean, so let us try write down the formula here again. Okay, which is summation from n equal to 0 minus 1 x n to the power minus I into 2 pi k n by n. So this is how xk, I mean the Fourier transform we are doing. Now let us compute let us compute x n minus k. So let me try to look at it. So what will be the value? So it will be 0 to n minus 1 x n e to the power I 2 pi n by n, and here in k, in place of k you will write n minus k. Okay, so this is capital N, total number of data point. Okay, so now if I calculate the value, so let me do it. 0 to n minus 1 x n e to the power. So for the first term, this n will be cancelled out. So e to the power minus I 2 pi n, and we will have multiply with the minus I 2 pi n k by n. But this term it will give me value 1. So because I mean this term is this term is I mean so since this is integer, so it will, I mean we can expand this cos 2 pi n minus I sin 2 pi n, and so since this is this is integer value, it will give me 0, it will give me 1. So effectively this term will give me value 1. So if I calculate x n minus, okay, so n, so x n minus k, then we will get n from 0 to n minus 1 x n e to the power I 2 pi n k by n. Now, if the x is a real valued signal, so so whenever we are doing an experiment or so on, so we are getting we will obviously get real value. So this x, generally in real world application, x is always real. So for real number, we can write this as x as x complex conjugate will be same. So for real number, we can write this x n minus k as x k inverse. So how we are writing this? So basically, we can put minus here and take the complex conjugate of the whole. So basically, that is why if we are dealing with a real valued signal, then we don't need to compute all the coefficients. So because now, so since this x n minus k and x k are related, so that is why you have to compute only one half of the spectrum. So and it is also important to know what is the what is the how much up to how much frequency you can extract. So for example, in your if your independent axis, so that scales from maybe 0 to t. So for example, up you are calculating up to 0 to t. So then you have to know about another important concept, which is sampling frequency and Nyquist frequency. So basically, up to how much frequency component you will know the information about system. So you cannot know about up to infinitesimal up to infinite frequency. So basically, so the idea is that your sampling frequency. So in your system you will have some largest frequency present, and your sampling frequency, so that must be at least twice at least twice of the largest frequency component. So in your system, if you are speculating that it has maximum frequency around 100 kilohertz, then your sampling frequency must be greater than this is must be greater than 200 kilohertz. So this is your sampling frequency, and so this minimum value, it is known as Nyquist frequency. So how why it is at least twice? So if you have, for example, you are getting this kind of signal from your system, and suppose your system is oscillating with this frequency. So if you want to truly replicate, if you want to truly replicate that this is the frequency that you are getting, so then at least you have one data point here and one data point here. So this is the minimum number of data point you need in each cycle. So that is why the two factor is coming. And if you have only one data point, so you will not be able to get this frequency. So the minimum frequency that you need is at least twice of the largest frequency that is present in the system. So if your system has largest frequency 100 kilohertz, so your sampling frequency must be greater than 200 kilohertz. So and that minim at that this should be minimum. So the larger you can go, that will be better. If you have larger number of data point here, so that will be good for you to replicate the actual behavior of a system. So this minimum value is called the Nyquist frequency. So now since now if we have our independent parameter in this range, then how can we get the frequency domain in our system? How can we get the frequency axis? So for example, we are getting signal. So for example, this is our signal that we are observing. So this is up to t time t, and this is at time 0. And your system, for example, suppose your sampling frequency is fs. Now how we'll get the so when you are performing this, so this is xn. Okay, so as a function of n, so it is going up to n. So when you are calculating this xk, so what should be the limit of k? So the k you will calculate in the following way. So you will start from 0, and so you will have a sampling frequency. So how you will get the frequency number? So basically you will multiply with this sampling frequency by 2. So you will multiply with sampling frequency. Then you will create an array which will run from 0 to n by 2. So okay. So this it will create an uniformly spaced array from 0 to n by 2, and you will divide this whole number by n. So in that way you will get the frequency axis. So effectively this will give you the frequency axis for plotting. So let me try to implement this in MATLAB and write a MATLAB code to uh, do the for fast Fourier transform. So this is known as fast Fourier transform. So here you don't have to compute all the n square element. So there you have this condition that n minus k is complex conjugate of is transpose a complex conjugate of this xk, and also so basically it replicates what is your system behavior. So the number of data point that you have to compute in case of this fast Fourier transform is it runs from it is scaled as n log 2n. So in DFT or discrete Fourier transform it scales as n square, but in case of fast Fourier transform it basically scales as n log 2n. So how can we write the fast Fourier transform code in MATLAB? So let me show you that. Okay, so let me complete. So let me give just write manual code first, and then I will uh, show what is the inbuilt function in MATLAB. So let me. Okay, so what? So first I will define sampling frequency, which is, for example, consider 1000. So corresponding to the sampling frequency, we will have a sampling period. So period is reciprocal of frequency. So this is sampling period, and you will have number of data points. So let me call it L. So this is the number of data point, and you will have your time axis. So let it runs from 0 to L minus 1 multiplied by T. So let me run it. Okay, so I have to write it capital. Okay, so you can see that our time array is created here. So for example, suppose this is our time array, and let me create a signal for this time array. So for example, let us create a signal where we will have summation of two sinusoidal components. So for example, f1 maybe 50 hertz, then we will have f2. Let us say this frequency is something around 200, and let us create the x vector. The independent vector. Let me give amplitude, then sine. We have to add the second term, sine to t. So let me look at the output. It is tx. So let me run it. Okay, so this is how our signal looks like. So maybe we can show you for once that this is a discrete stem plot. Okay, so this is the data point we are getting. So with time, so I mean, so this signal that we are getting, so we know that it is a summation of two sinusoidal. Now, suppose you want to compute the DFT manually, which we have, I mean, written earlier also. So let me just write it. So n to x, and so for example, in x we will store the uh, what in the computed value using the Fourier transform. So call it x manual, and let me pre-allocate here 1 n. Then now then what we'll do, so we'll, so since I mean in case of DFT we have to store we have to compute this one. So let me write down it. So and we have to run another loop, and since we have to write here x a plus 1. So since you are starting from k0, so you have to put here k plus 1, which will be x manual a plus 1. So since you have to summation, so we have to, here what you have to write, so here we will have x n plus 1, because I mean n is also starting from 0, and here we will have the exponential term which is minus 1 j 2 pi k n divided by n, and let me end it, and there should be another end for this follow. Okay, then you have to, I mean we have to define we have to specify what is the frequency axis for plotting. So I mean if this is my time data, so then what is the, so when you are I mean converting in frequency domain, then what is the frequency axis? So frequency axis you know is will be defined like this: f equal to, so our sampling frequency, and we'll multiply that with 0 to n by 2, that will be divided by n. So how, what is the maximum frequency that we will go? So because I mean we know that so the sampling rate is 1000, so the maximum frequency, so here if you put it here 1000, so the last, for the last element, so it will run from 0 to n by 2, so it will be fs by 2, so the maximum frequency we will get is 500. So I mean that is the Nyquist frequency. So if you are sampling data at a frequency of 1000, so if you are acquiring 1000 points in 1 second, then in the frequency domain, according to Nyquist theorem, you can go up to 500 hertz. So that is why I mean, and we will have to define frequency axis in this way, and then how so then and also what you have to do, so you have so here you are storing what is the transform value, Fourier transform value, and it has so it is a complex number, so it has real number and imaginary number. So we have to take, I mean, if you want to know what is the magnitude, I mean, if you want to plot only the magnitude, then we have to take absolute of this number. So let me write it. Call it P2. Is manual. So I have to divide it by n. And since, I mean, so there is this, I mean, symmetry in the x n minus k and xk. So I mean, we can write down P1 from 2 to n minus 1. So that will be 2. So this 2 factor is coming due to the energy conservation. So that will be multiplied with 2. Okay, so first we have to define what is P1. So P1 is basically P2, and we are folding it. So because it has this symmetry, so folding, I mean, we will do it in this way from 1 to n by 2 plus 1. So we'll write n by 2 plus 1. Here we have to write, and I mean, so this 2 is coming due to the energy conservation. So since you are only taking one half portion, so I mean the in your original signal and the Fourier transform signal, which is now P1, so that doesn't have the same energy. To, and you also know that I mean, it is symmetric. So if you want to conserve the energy, you have to multiply it with the factor of 2. So let me do that. P1. Okay, so the P1 is the Fourier transform of the upper order signal. So let me plot it. Figure 1. Let me plot figure F P1. Maybe 1.5. Okay, so now let me run it. So it should give me what is the Fourier transform output of your original signal, but it is using the DFT function. Okay, so now I mean, we can increase the number of data point, because as you can see that we have this 200 and this 50 hertz frequency component present. So, I mean, if you change it to a different value, so it will give me the corresponding frequency component. And how far we can go? So you can go up to 500, because our sampling rate is 100. So I mean, if you I mean, if we check with a different frequency, then it will not give us the desired one, because I mean, the Nyquist frequency. So if you have 1000, I mean, so your sampling frequency, if your sampling frequency is fs, then the maximum frequency that you can get from your signal, I mean, which you can extract, is fs by 2. So that is why, I mean, if your system has some different frequency, for example 800, and if your sampling rate is 1000, so your FFT will not give the accurate result. So I mean, you can show here that it is showing 100 and 200, but which is not the case, because I mean, so that is why your sampling frequency is important, and it should be at least twice. So let me make it twice. So this is the maximum frequency component present. So for 50 it is showing okay. So let me show you. So it is still at the 51 is okay, because to resolve the 50 hertz component, you need at least fs to be 100, and our fs is 1000, so which is greater than 100. So that is why it is good. But our second frequency component that is present is 800. So to resolve this 800 frequency, the minimum sampling rate that you need is 1600, but here it is 1000. So that is why it is giving incorrect result. So let me make it now. So it is still giving incorrect result because I mean 800. So you have just make it twice. So you can try to increase it. Okay, so now you can see that it is actually showing what is the frequency component that are present in our system. So that is why it is important to know what is the to guess, or I mean if you are working with the system, so you must first speculate what should be the maximum frequency that you are dealing with, and try to make the sampling rate I mean at least twice of it. So it will be good to increase the number of sampling rate. And to compute the FFT, so this is how the DFT is being performed, or the discrete Fourier transform. So for fast Fourier transform, there is an command in MATLAB. So let me show you FFT. Okay, so the so here we are writing this code. So this one is to calculate the Fourier transform, but we can just do it with this FFT command. So we can just write down here instead of this X manual and so on. What we can write down? So instead of this portion, we can just write here FFT of X, and let me comment it. Yes, let me write X manual FFT, and let me write it here again. P2 FFT, P1 FFT, and it should be P1 FFT. So let me put hold on here, and I'll plot now F with P1 FFT. So if I do it here and let me run it. Okay, so you can see that it is actually giving us the same result. So for that you can pause here for 2 seconds, and you can see the output. So this is using DFT and this is using FFT. So it is the why the fast Fourier transform is good, because it uses less computational power. Because instead of dealing with this n square number of data point, so for DFT you deal with n square data point. For FFT you are dealing with n log 2 number of data point. So this is, I mean, for small number of data point you will not see too much difference. But if you are dealing with millions of data point, trillions of data point, so in that case, n square and n log 2n, they have very large difference. So that is why FFT is very widely used, and for doing this for Fourier transform, and because it uses less computational power, and it I mean use symmetry operations. So I mean, so it basically uses some trick. So it the so it is not any different kind of transformation. It is still the Fourier transformation, but instead of calculating all the xk point, you know there are symmetries present, so you don't need to compute all the data point. So some data point, I mean, you can infer by using other data point. So effectively, you will have to I mean, it has to compute less number of data point. So that is why for large value of n, it is very effective and useful. So I mean, and this you don't have to worry about how to how you don't have to worry about writing this. So basically, so you have to just write down the FFT command, which will give you the FFT, and you can look at this manual FFT, X manual FFT, and X manual. So this is the value you are getting from using this discrete Fourier transform. and this is the value you are getting from using first Fourier transform. So values may be a little bit different, but you will not see any. I mean, so as far as the frequency component is concerned, so whenever you are working with this Fourier transform, I mean, you want to know what is the frequency component in a signal. So as far as the frequency response is concerned, so you will still know what is the frequency value that is present in a system, but with very small computational power. So I mean, it is computational less heavy, very less heavy, and it gives you almost accurate result. So that is why I mean we so generally this FFT is mostly used. So after that, so I will solve a harmonic oscillator problem, and I will show it how we can how we can look at the response in the frequency domain. Okay, so now let me show you how you can use this FFT and solve damped harmonic oscillator equation. So let me start from from the scratch. So suppose this is our system. So we have for example, consider a damped driven harmonic oscillator. So we have the equation to be m double x dot plus cx dot plus kx. So this is the damping factor. So this is damping coefficient, and here so if you can have the drive here, or so let us consider the drive. So so for example, it is driven. So and this omega d is the drive frequency. So let me write what are the parameters here. So k is the spring constant, then we have omega d, which is our drive frequency. This is the mass, and we have f0, which is drive amplitude. So here this is our periodic driving force. So this is the frequency of the drive, this is the damping factor, and this is the spring constant, and this is the mass. So we can transform it. So so we can define natural frequency. So natural frequency is generally defined as root over k by m. So we can write, and also let us consider a factor called damping ratio. So which is, let us call it gamma or xi. Let me call it xi, and it is c by 2 root over km. So if I substitute it here, then our equation will be look like this: x double prime plus 2 xi omega naught x dot plus omega naught square x, and here we have f0 by m cosine of omega by d omega d by t. So this is your equation of motion for a damped harmonic oscillator which is driven. Now let us try to solve it and look at the response of this in time domain and also in frequency domain. Okay, so let me proceed. So let me just first write down clear all, increase the size a little bit, CLC. Yeah. Then we will define parameters of the system. So what are the parameters? So mass, let us take to be 1. Then we have spring constant. So for now, let us consider it 10. We have damping coefficient. So let us take it to be 0.5. And then we have this parameter, so natural frequency, which is omega n. That means omega natural. And what is this omega natural? So it is defined as square root of k divided by m. So this is our natural frequency, and we have the zeta term, so which is, let me look at it. So zeta is defined as c divided by 2 root under km. So it is defined as c, which will be divided by 2 multiplied with square root of k multiplied with f. So this is our zeta, and then let us specify our time. So first let us look at what is the natural frequency. So let me run it. Okay, so natural frequency, I mean omega is 3.16. So I mean this is the angular frequency. So radial frequency will be around, I mean, so if I'm divide it by 2 pi, so it will be around zero point 0.5. So I mean, so in 0.5 second it will complete one cycle. So let me take time to be around maybe up to 20 seconds. So that, I mean, we will I mean the transients may die down, and after that system will be in the steady state. So let us define our initial time. So this is our initial time, then we will have our final time. So let us take to be 20 seconds. Then we have the time step. So in one cycle it is completing, I mean, in it is completing one cycle in around 0.5 seconds. So I mean we have to make dt less than at least 0.25. So let us make it 0.01. So that is an Nyquist theorem. So you have to be careful what is your dt. So I mean from omega n, I mean, so from, you can look at what is the natural radial frequency of your system. So it will be 2 pi, so that will be around 0.5. So Nyquist theorem says that your dt should be less than 0.25. So let us consider it to be 0.01. And now we will define our time axis, so which will run start from t0, and we have here dt, and then we will simulate it up to tf. Then we have so we have to find what are the data points, how many data points are there in t. So for that we have to write in n, which will be length of t. So let me save it first. So let me run it. So this will be lecture 7. Damn it. Okay, so we have 2001 number of data point in our system. And then what we have to define? So I mean, since this is a second order differential equation, we want to solve it. So we have to define some initial condition. So we will write down the initial conditions here. So what are the initial conditions? So we have x0 to be 0. So consider it 1, and we have v0 to be 0 for now. Okay, so this is our initial condition. So I mean we will define an array. Now what you have to do? So you have to store the values of position and displacement, position and velocity. So we have to create an array. So let us create the array. So creating displacement and velocity array. And here what we will do? So let us call it to be x, which is our uh, displacement array, and it will be like zeros. And what will be its dimension? So it will have one row, and there will be n columns. So n is the length of t. Similarly, you will have array corresponding to v. So let me save it, let me store it in and call it v. So this is our displacement array, and this is our velocity array. So right now it is all the elements are 0. Now we want to store the initial conditions. So what do we have to do? So the first element of x, that should be x0. So here we are storing it, and the first element of v, that should be v0. So here we are storing the initial condition for velocity. Now, I mean, since this is a second order differential equation, so we have to specify our equation as first order. So what will be the equation? So one is dx dt equal to v. So this is one equation, and we have another equation which is dv dt equal to uh, what should be the equation? So if I omit the drive for now, so let us consider f to be 0. So here we will have minus, minus k by mx minus c by mx prime. So minus c e, and then we will have minus k x, and it will be divided by m. So this is the equation which you want to write. So let us define these functions. So, or you can, we can go to so since we have already created that, so we can go to our MATLAB online, and we can try to search that. Or we can write, so we can write one from scratch on. So let me define the function. So you can define in this way also. So here you will have x p. So you are specifying MATLAB. So so here that x and v, these are variables. So you are specifying MATLAB to consider this as variable, and that is you are writing under this character. So this is your one function, and you will have your another function, and it will here also this x and v will be variable. So you have to specify that v, and what is your function? It is basically minus. So this is your functional form. So minus kx minus k 3v, it will be divided by m, and so this is your function. Now, so you can solve it with RK4, or so let me solve it with RK4. So you have to run a loop for 1 from 1 to n minus 1. So n is your length. Yeah. So for I equal to 1 minus 1, so first you have to do. So let me specify what is k1x. So this is the, so we can do it from the way we have done in the online the last class, or you can write in this way also. So it will be dt multiply with the function, and what will be this, and you want to evaluate this function at xi and vi. So this will be a k1x. Similarly, you will have k1v, which will be dt g, and here also you will evaluate at xi vi. So let me pass it here. Okay, so this is your k1x and this is your k1v. So let me close, let me suppress the outputs. Similarly, you will get k2x and k2v. So you will have k2x, k2v, and what will be k2x? So it is basically evaluated dt at what will be xi, so xi, and here you will add 0.5 multiply with k1x, and similarly here you will add into 0.5 into k1v. So this is your k2x, and for k2v, evaluate, so here in place of f you will have to write g. All the other terms will be same. So copy it. So here you will evaluate the function g at xi plus 0.5 k1x and vi plus 0.5 k1p. So similarly, in the same way, you can calculate k3v and k2 k3x. So we have here k3 and this will be k2, this will be k2, here also you will have k2, this will be k2, this will be k3, and after that we will have k4. So it will be k4x v k4, and here instead of in place of 0.5 you will have 1, here also you will have 1, this will be 1, and it will be k3 k3, this will be 1. Okay, so I mean we have calculated uh, all the vectors for this rk4. So after that, what we have to do, so we have to update our x value and y value for the next loop. So here, what is the update tool? So xi plus 1 should be equal to xi plus dt divided by 6. Because dt you have already put in all this. So this dt, I mean, we don't have to worry about. So xi plus 1 by 6, and here you will have this k1x plus, so here we will have 2k2x. So let me just copy it. Will be 2k2x. Then we will have 2k3x, and then we will have k4. So this is the update tool for x. Similarly, we will have update tool for v also. So here you will have v. This will be v. Here we will have v. This will be v. Okay, so in this way you are updating what is your x and v value for after each time step. So basically you have gotten your position and velocity. Now if you want to plot it, so what do you have to do? So let me plot it in figure 1, and let me plot both of them in a same figure. So we can call subplot. So subplot, and here we will have 2 1 1. So I mean for subplot, so this is the, I mean, in how many columns you want in your plot, and the second one is how many sorry, this is the how many rows you want, and this is how many columns. So basically it will so let me just plot it and let me show you. So you will plot t with x, and let the line width to be 1.5, then uh, x level. So in x-axis you have time, and in y-axis you have displacement. Then you have your subplot 2. So let me copy it, and two second uh, 2 row and 1 column, and in the second position you want this. It will be V, and let me run it. Okay, so I'm able to perform because left and right is again. initial condition, creating arrays here, the initial condition. Okay, so here it should be dt. So now, yeah, okay. You can see that how the velocity and displacement changes as a function of time. So let me call it velocity. Okay, so this is how the displacement is changing. So we have set the initial condition to be 1, and since there is no drive present, so ultimately due to the damping, so it is effectively uh, going, its displacement is going to 0. Now what we can do, so we can do the FFT of this. So, and how the subplot is working, so basically the whole this figure, it is dividing it into two row. So there is this two row and one column. So if you have written here 2 2, so it will create space for four figures. So let me show you if that is working. Okay, so this is the two row and two columns. So it has created the whole. Let me run it again. Yeah, so you're specifying that divide the whole figure into four portions, and in the first figure you should. So this is the number of rows. So there will be two rows, space for two rows, and space for two columns. And in the element, in first element you plot this, in second element you plot this. So you can plot multiple things in the same figure also in this way. So okay, so this is with a subplot, and now let me show you how you can compute the Fourier transform of this time series data. So how can you perform the Fourier transform? So we want to get the frequency domain now. So what will be the for Fourier transform? We know that we have to write this FFT. So this is the command for doing FFT or fast Fourier transform to any data, and how you will get the frequency axis. So frequency axis, we have learned that you have to write down this. So it will start from 0, then you have to go up to n minus 1, and so what is the sampling frequency? So sampling frequency is basically uh, inverse of dt. So this is your the difference between two data point. So inverse of that should be the sampling frequency. So let me call sampling frequency, which is 1 by dt, and let me write down fs here. So here we will have fs, and the whole thing will be divided by n. Because in this way you have gotten your frequency axis also. So now what do you want to do? So again we have to take the uh, uh, we have to do the rest of the things. So we have to take only one side of the spectrum. So let me write down x magnitude, which is absolute of x, which will be divided by n. Then we will have, then what we will do? So basically we'll write this again, x magnitude, and here we will have x magnitude, and you want to just fold the data. So you will start from 1 and you will go up to, so you have to write the floor function, because if n is odd, then you have, so for n odd, if for n by 2, that will give you not an integer number. So you have to put the floor function, so n by 2, and after that you have to again define the frequency axis, which is, I mean, you have to go up to n by 2. So let me write down here, start from 1 and will go up to floor n by 2. Now you want to plot this, so let me plot it in figure 2, and here you will plot what? So let me plot here, plot x axis is your frequency axis, then you have x magnitude, and so let me plot it. Okay, so you can see that this is the response of the system. So frequency we are getting around zero point 0.5, and so I mean we have calculated this natural frequency by 2 pi. So what it came out? So omega n divided by 2 multiplied with pi. So it is 0.05, 0.5033. So almost so the frequency is giving right. Now suppose you want to limit, you want to change the x limit, because let me show you the output. If I just run it, so it is, I mean, going up to 50. So now we can change that. I mean, we can change the, so x limit. You can just look data from 0 to 5, and you can run it. You can see that this frequency is appearing around zero point 0.5. And also, I mean, you can plot your y-axis. You can put up you can set your y-axis in log scale. So for that you have to write this command, set gca, then you have to specify your y-axis. Okay, so you have to write here y scale, I guess. Let me check. Then you have to write that you want to set it in log. So let me run it. Okay, so what I yes, so GCA maybe should not under this string. Yeah, so you can see that now the scale, if you look at the y scale, so this is log scale. So I mean, if you want to compare data where this, so for example, and why this log is useful. So suppose you want to plot multiple data, and I mean multiple plot, and for each plot, so they are, I mean, the y values are order of magnitude different. So if you plot that in linear scale, so that will not give you, I mean, visually you will not be able to observe the trend in in each of the region. So for example, you have one linear variation, one the y equal to mx, and in another axis you have y equal to x to the power 5, and you are plotting up to, so let me show you quickly. So let me, x is from 1 to 100. We have y1, which is x, and we have y2, which is x to the power 5. Now if you want to plot both of them, so x y1, then you want to hold on, then you're plotting x y2, and if you run it, okay, so element wise operation should be done here. Okay, so you can see that there, I mean, we are not able to see the linear variation, because I mean, for it the value is 10 to the power 9, and I mean for it is 100. So you can try to, so here what you can do, so you can set the y scale in log, and you can try to look at the variation. So now you can see that you are able to see what is the variation, but it is in log scale. So this is 10 to the power, so this is 0, so this is 100, this is 10 to the power 4, this is 10 to the power 6, but you are able to see the variation which you are not able to observe in the case of linear scale. So that is the use of y scale. So now let me go back here and suppose here also suppose you have a drive present in a system. So what you will do? So this for example, suppose you are directly driven your system. So you can add the direct drive term here. So let me try to do that. So let us call the direct drive strength to be f0, multiply that with cosine of omega d multiplied with t. So we know what t is. Now we have to define what is f0 and what is omega 0. So omega d. So omega d, let me take something to be 2 pi, and let us take f0 to be 1, and let us try to run it. Okay, so let me see. So this is that's the dot is operation that is from. So Cv minus kx plus a0 usually multiplied with cosine. Okay, so not problem of the next one. Okay, so since you are defining t here, I guess maybe you have to pass t also, and you have to pass here ti. And for the next one, you have to write ti plus 0.5, that will be multiplied with dt. So you have to write this in all the cases. Here incorporate here, 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 here. Okay, so now let me check. Fine. You can see that the response has now changed, because in the system, so there are two components of drive. So one is the natural frequency component. So you can look from the frequency domain response. So you can see this is the natural frequency, and this is where you are driving the system. So let us try to increase the strength of the drive. So let me make it, so for example 5, and let me try to run it. Okay, so you can see that the response is increasing, and if I look at it, so yeah, so it's display in displacement also you can see the variation. Now we can do this for a array of f0. So f0 array, we can start from 0 and go up to steps of 0.5, we can go up to 5, and this will be the same for each of the cases. So creating displacement, and this will be the initial condition for all the one. The function will also be the same. Okay, So function will change. So f0 value, so that, so from here you can insert the loop. So for f0 equal to 0 array. So f will take points from here, then it will define the function, it will calculate this, it will plot, and so we can write here hold on, can insert here hold on also, and we can insert here hold on, we can end it. So run, yeah, you can see that with increasing, you can see that with so let me pause in each of these so that you can understand. So hold on, then maybe pause for 1 second, then pause here for 1 second also, and also pause here for 1 second, run it. Okay, so you can see that it is updating slowly. So I mean the dive strength is increasing, and corresponding to that how the system behavior is changing, that you can observe in this here in the graph. You can see that the frequency component at this at this dive strength is increasing, so the amplitude is increasing here. Okay, so this is how your system response will change with increasing diving strength. So I mean, so you can create a 3D plot also. So I mean, you can look at the also you can store the what is the displacement and position values for different directions. So I mean, here you can, so in place of one, you can write down what is the length of your uh, F0 array. So length of your F0 array. So you can also replace that here. So this and now this will this arrays are created using and so here you have to specify the, you will store this initial condition in all the rows. So let me write down here all the rows, and here you will have this function. So I mean, and so here also you have to specify what is the uh, I mean row value and column value and so on. So once you are done with it, so you have find out what is your x array is, and you can store it here. So along the, so for example along x zeros 1 n, you will store the x and b after the first loop. Then in the second loop along the second array along the second row, you will store the displacement and position value. So in that way you can store all of them. So I mean, and if you want to further analyze it, so you can analyze it with that. So okay, so let me just return to the previous case, what it was. Okay, let me run it. Okay, so this is the response of your system. So I mean, this is how you will be. I mean, you can work with this harmonic oscillator system. So this is a damped harmonic oscillator system. So here you can, I mean, introduce cubic terms. So which will, so if you put something like x cube, so that will effectively make your system nonlinear. So this is your nonlinear harmonic oscillator system, and you can look at the response. So with increasing time step. Let us look at it. Okay, so there is not much significant difference because I mean, so your nonlinear coefficient is not too much. So here you can introduce some nonlinear coefficient. So you can make it 1 5. I mean, or you can try to increase it to check for to I mean to look for the effect of nonlinear response, and we can I mean write a C now. So it is almost diverging. That is why your system is not giving you any result. So it should be less than 5, and if I run it, so it is still diverging. So I mean in the next lecture, so we will learn about this nonlinear oscillator system. I mean how nonlinearity can arise in such system. So for now, let me just clear all CLC and let me run it once again. Let me pause it for now. Zero. Stop. There's the minus. Okay, fine. So, I mean, we have learned how we can simulate this uh, damped harmonic system, and also how we can look at their frequency response. So, in the next lecture, I will introduce you to the to this nonlinear harmonic oscillator, and I mean why nonlinear, how nonlinearity can arise, that I will discuss. So, I will discuss some cases where like a string maybe. So and then also from Taylor series expansion from the I mean you will see that I mean for very small displacement of this oscillator system it is linear, but if you consider the displacement to be large, then inherently the nonlinear terms will come into play. So you will play with this nonlinear oscillator system, and I so which is basically known as damping oscillator system. So so today we have I mean learned about how to plot, how to look at how to do the FFT in MATLAB. So there is this inbuilt FFT command which you can use, which is basically the fast Fourier transform. And then we have looked at how we can solve the how we can look solve damped harmonic oscillator system using FFT and look at its frequency domain. So that is it for today. So we'll see you. I'll see you in the next lecture.